Today we are looking into a new chapter of the fuzzing book, namely Concolic execution. With this chapter, we start going into so-called symbolic execution. That is, we look at the conditions that we have in the program code, and we try to solve these conditions in order to cover as many paths in the program as possible. Concolic is a combination of concrete and symbolic. And what this exactly means, we're going to go into this right away. Concolic fuzzing. What is concolic fuzzing all about? Concolic fuzzing means that we're actually using program analysis to find out which parts of a program to execute. And the idea is to collect constraints and conditions while the program is executing, and then systematically negate these conditions in order to find different branches. For this, let us go into a very simple program, namely the triangle program. We have a small program here which is called the triangle program. This is a classic in testing because this is actually a program for which we want to find out the properties of a triangle. So this is the triangle program, and this triangle program gets three lengths A, B, C of a triangle, and then it returns the class of the triangle. Namely, either this is an equilateral triangle, equilateral meaning that all three sides, lateral, Latin, equal. What is Latin for equal? Equus. No, equus is horse. I had Latin. I should know the word. Equalitus? No, equal, whatever. Okay, good. Simply means that these three sides have all the same length. And then there's isosceles, which means that at least two sides have the same length. And then there's scalene, which means that these three sides all have different length. And this is all there is in the triangle program. So if we put in 1, 2, and 1, for instance, we get a triangle isosceles, which means that there's two with the same side. But if we put in triangle 1, 1, 1, then this means that the triangle is equilateral. Okay, that's very simple. So, and you can see that in this program there's a number of conditions. So if A and B have the same value and B and C have the same value, then it's equilateral. If that's not the case, but at least B and C are the same, or A and C are the same, then at least it's isosceles. And if all three are different, then it's scalene. Okay, and what we can now do is we can go and test this triangle program using our Concolic fuzzer. And for this, I'm going to show you how this actually works. Let me go a bit down into the code in order to get right to the example. Now we have a particular class, the Concolic Tracer, which executes a program, and while executing the program, it actually tracks all the conditions the program goes through during this very execution. The way we use this is as follows. A Concolic Tracer comes in a with block. We have seen this for other tracers as well. And we typically give it a very short name, such as a single underscore. And then we invoke individual functions. However, these individual functions that we have here need to be specifically translated, namely, and we do so by using the Concolic Tracer with the function name as an argument in an array access. So we use this to get an item, and then we can just invoke the function as normal. What this underscore, what this square brackets thing here does is it replaces the original variables by so-called shadow variables, which, like the information flow that we have seen in the last chapter, tracks extra information. So but other than that, we can just execute it as normal, which we do in here. So we just execute it. And then after we have executed, we can retrieve a couple of extra information. So first thing what we can do is we can retrieve the actual so-called symbolic variables. So we can find out that the triangle program works with 3 variables, namely A, B, and C. Well, we knew that before, didn't we? Okay, so that's great too. Yeah, so it's going to explain me what a triangle is. I think I'm going to switch this thing here off. And 3 minutes later, I'm actually going to get this. Timeout in 10 seconds. I'm going to sing The Girl from Ipanema again. Here we go. Wonderful. Okay. The interesting thing is this thing here. This is the path the program has taken. And here we see the individual conditions that have been, that the program has collected over time. So what we see is that it is not the case that A, which we have here, equals B. It is also not the case that B is equal to C. And it also was not the case that A was equal to C. And if we invoke the whole thing with different numbers, let's just do this for fun for just one time. So let's put in a triangle with A, B, C. This is an equilateral triangle, as also confirmed by the triangle program. We still have the very same variables as before, but now we have taken another path, namely now that the conditions are that all these values A and B and C are equal. And these are conditions that actually change the behavior of the triangle program, because this means that now different paths in the program have been executed. Okay? And interestingly enough, we can now go and change these individual conditions too, and thereby create new values for testing. So let's get back to our original example here, because I'm going to need that one more time. So again, 1, 2, 3. So this was the scalene, and we have seen that we now have conditions that actually show that it was not the case in the program during the execution that A equals B. It was not the case that B equals C, and it also was not the case that A equals C. Now what we can do now, in order to test the program thoroughly, is to take these conditions, A equals B, or actually not A equals B, and negate them. So what we want is a test case where A equals B, and then if A equals B, then we're going to take a different branch in our triangle program, because the condition will be different. Normally, we would now go and say, okay, let me think hard about 3 values, A, B, C, where A is not equal to B, where A and B are equal, but where A is equal to B, but C is different again. Oh, let me think hard. Can I think of 3 such values? Okay. Well, it's actually not that hard. But the nice thing is we can automate all this by using a so-called constraint solver, because we can take these constraints or different constraints and put them into a solver program, and the solver program will automatically determine values that fit these constraints. For instance, if we take these very constraints, as we have them in here, if we feed them into a constraint solver, we're using the very famous and very popular Z3 constraint solver from Microsoft here. What we get is a result. The solver can go and satisfy these constraints. Well, it's just 3 of them. And it can solve these with 3 different values. Namely, it says that if we put in A, with a value of 0 and an integer, which is an integer, and b with a value of -2, and c with a value of -1. That's actually a solution for the constraint up here. You will notice that 0, -1, and -2 are not exactly correct values for the length of a triangle, because triangles very obviously have positive lengths. So that's not that's a bit of a surprise here. But if you look at just the triangle program, then indeed, if you give a and b and c these three different values, then again you're going to get exactly those constraints, and you also are going to get the exact same result. Because if you do that and invoke the triangle program, yes, you're going to get scalene one more time. So we're having constraints, and you can solve those constraints. And if you solve those constraints, you're going to get a solution that takes the same path as originally encoded by these constraints. And now the fun thing is, what happens if you negate some of these constraints? For this is also here in the example, we create three new integers, or we create three integer variables, namely ZA, ZB, and Z3. ZA, B, C, ZC. Here we go, and this is triangle A, triangle B, triangle C. And now we say, okay, I want to solve all this, but I wanted to replace one of my constraints, the first constraint, namely, which we have up here, namely not B equals C. I want to replace this one by B equals C. Okay, now we're having B equals C, and I want to solve this. So can we find a solution for that? And it turns out we can, or at least I hope it's going to turn out we can. Here we go. And we have a value of A being 1, B being 0, and also C being 0. And if we put this in here, 1, 0, 0, then we get, oh, now we have an isosceles triangle, which is very nice. Now we can also put in more constraints in here. So let's say we also want A and B being equal. What's going to happen now? I don't know what's going to happen now, but I have an idea of what's going to happen. If we say that A and B should be equal, and B and C should be equal, we're getting no solutions. Why are there no solutions? Because now I have said, because we still maintain the original path constraints, and now we have a path constraint. The first path constraint is A equals B. Second path constraint is B equals C. And our third path constraint is still in here, namely A and C should not be equal. And if we tell it that, but if you tell it that A is equal to B and B is equal to C, but A and C should be different, then this is not solvable. This is mathematical impossible. So, but of course, we can negate all the conditions. So we can say, okay, let's give it a third condition, namely A and C should also be equal, and then we're going to get a constraint that tells us the value of, what is it, 0, 0, 0? Yes, it's 0, 0, 0. Okay, and the triangle of 0, 0, 0, of course, is equilateral. Equilateral in the sense of the triangle program, that is a real triangle with three sides with a length of 0. Yes, it is equilateral in the sense that a point is also equilateral, but at this point we are definitely leaving our application domain, and we're only talking about the triangle program and its outputs. Okay, so this is what we're having here is two things. We're having one mechanism that gets us individual constraints, namely the constraints taken in our program, the path conditions taken in our program during an execution. And the second thing we're having is a constraint solver that can take such constraints or modified constraints and actually by negating them take different branches in our program. And now you can do this systematically and try to negate more and more branches, one after the other. And then you start with a concrete execution. You collect all the conditions, and then you're going to take all the alternate branches as well. And this is also something we have implemented in a so-called Concolic Fuzzer, which actually builds on these, this tracer, as well as the constraint solver, these three constraint solver that we've seen, to systematically explore all branches of a function. Having said that, the question is again, how does all of this work? First thing, how does a constraint solver work? We are happily deferring all of this to advanced lectures in automated theorem proving, because this is actually going to be a study in itself. At this point, we're simply assuming, oh great, we have a constraint solver, we give it a bunch of constraints, and we automatically have it solved. Problem solved. It's like an operating system. See, it's there. Yes, we can open files. Yes, we can access individual elements on the network. But studying how everything works below that layer is a separate part of study by itself. The other interesting question, however, and this is for us, is how do we collect these conditions during an execution? And this is where our previous knowledge from information flow comes in handy, because very much like in the information flow chapter, we collected taints that were then propagated. We here expand Boolean values and integer values to also collect the conditions they are being used in. And I'd just like to give you a short pointer to the respective important parts in here. So we call these Concolic proxy objects. This is the reason why you should first look into the usage of all of these parts before understanding how all of this actually works. We're having these so-called Concolic proxy objects, which allow us to track all this information. So, ladies and gentlemen, how this whole thing, the way this whole thing works is as follows. Very much like we had the T-string and O-string classes in our information flow to track additional information, we are creating special wrappers around Boolean objects and integer objects in order to track what's going on. And what we're having here is a bool, a z-bool, which is the equivalent of a Boolean in our execution. And it has three elements. The first element is the v element. The v attribute contains the actual value, which is true or false. The z element, the z attribute, contains a condition that actually was used to form the Boolean object. And finally, we also have a context in which we save all the Booleans that we actually came across, which means that while we are executing, say for instance the triangle program, every Boolean, every time we instantiate a Boolean, for instance to solve the if condition, then this code automatically gets executed. This is the whole idea in here, and this is. So what we're saving here is variable names, and as things get longer, entire conditions. We also save the actual value encountered, and this is what we then put together to form these path conditions. And very much like with our information flow string class, we have to implement extra operations. So we need to make sure that if we negate a bool, then we also keep all the information that is attached to it. So we propagate this information. So we can see here that if we go and negate our original my boolean variable. Then z, that is the symbolic part, actually now contains not my boolean argument. So you see that we are working with symbolic expressions here, and we keep on expanding these also when they get evaluated as conditionals. Then we are putting things together. And so, for instance, if we say we want to compare two variables, integer variables, say a variable a, symbolic, and a variable 5, then this also becomes a condition in the end. What this implies, though, is that not only do we have to wrap booleans, we also have to wrap all the integers such that they also are treated symbolically. We also have to wrap strings. Actually, anything, any data object in our program has to be wrapped accordingly, such that we always can keep track of both a symbolic representation as well as a concrete value representation. And this mix of a concrete value and a symbolic expression that we track during the execution, this is what makes the word concolic, as a combination of the concrete value, as we have it up here, and the shadow symbolic variables that are with these symbolic expressions that are attached to the concrete values and get propagated during the program execution. And this is how we can then create these complex expressions, these complex path conditions in our program, and this is how we can then negate them and finally feed them into our Z3 into our Z3 solver. And this is how, starting with a single input that executes the program and takes only a subset of paths in something like the triangle program, we can then systematically explore all the individual branches in that program. So, isn't that just beautiful? Lots of effort, lots of things to be done, but also, let's not forget, important limitations with all that. Because, you see, for one thing, this requires that every single data object be wrapped in an appropriate container that also tracks all the operations that were done on it. That's one thing. That's still feasible. It hurts performance, but it's still feasible. The bigger problem is that how many constraints can a constraint solver actually solve? And as program executions get larger, so does the number and complexity of constraints. And you will find out that symbolically executing a program, or more precisely solving all these path constraints symbolically for a large number of complex constraints, you're very, very quickly going to find the limits of what a constraint solver can actually do, well, in finite time, meaning your lifetime. Constraint solvers are immensely powerful, in particular things like Z3. That's just a miracle thing. On the other hand, well, you will also quickly reach their limits. So the general assumption is, when you're working with constraint solvers, or generally with symbolic computation, you use the symbolic computation in the small for individual functions for which it is relatively easy to explore individual paths. And for anything else, you use a regular fuzzer or a regular test generator, be it grammar-based, be it evolution-based, whatsoever. The nice thing about concolic fuzzing is that it allows you to execute a single function symbolically in a concrete context. So in this concrete context comes from the concrete values used by test generation. So you have all these concrete values. Now you're having this individual function that is invoked in this concrete context. And this is where you can then do symbolic reasoning in the small and still explore a couple of extra branches. So when do you do such concolic fuzzing? Either you combine it with a regular fuzzer for the last mile, for the last individual functions, for anything your fuzzer hasn't found yet, then you can throw a concolic fuzzer at it. That's number one. Number two is you're having a program where security and reliability is paramount. So suppose you're building a space probe that you're sending off to Mars or somewhere else. This is, of course, where you need the absolute maximum in terms of reliability because, well, you cannot simply go there and press a reboot button while it's navigating to find its orbit around Mars. So, and this is if you have plenty of CPU time available, this is, of course, when you can also use such concolic fuzzers even for larger programs in order to try to execute as many branches as possible and in order to find as many bugs as possible. Having said that, modern concolic fuzzers are actually being used all across large-scale software enterprises. Microsoft uses concolic fuzzing a lot in order to test device drivers and other parts of the Windows operating system. Amazon uses concolic and symbolic testing techniques in order to verify instances of its cloud storage system. Google does concolic testing. So if you have infrastructures that really need to work and really need to be secure, yes, this is also your stuff. If you plan to explore this chapter, go ahead and first focus on the usage, then dig deeper into how concolic tracing works. Using the Concolic Tracer class uses plenty of pretty advanced Python hacks, so you may need to dig deeper into how these actually work. And if you want to build your own concolic fuzzer on top of that, you take the Concolic Tracer class for granted and build on that, because that's arguably one of the most complex parts of the entire book. Enjoy concolic tracing. Enjoy one of the most advanced methods of testing that man has discovered so far. Have fun hacking, have fun testing. Thank you very much.